Can you see that? Sick. Okay. Before I get into that and the different types of analysis, I just wanted to revisit. So the analyses that we did last week are all linear static analysis. And so with FEA, there are a literal just Russian doll assumptions that you are baked into that. FEA, of course, in of itself is an assumption and is an analysis method. It's like it is an approximation of it. So that comes with some salt. When you are doing linear static analysis, like both linear and static are also assumptions you need to keep in mind. And these are not ordered in any hierarchy, by the way. Like these are just assumptions that are there. And I'm sure there's a million other ones that I'm not even touching on. But again, grain of salt with all of these, and you need to be aware of what analysis you're doing and what assumptions come baked with that. For linear, that first one we talked about, this is the cantilever beam we did last week, just real simple. A linear analysis assumes that the entire structure in all directions follows Hooke's law, meaning that like F equals KX. What's up?
The stress is directly proportional?
Yeah, that should say stress is directly. Strain is proportional to strain. It is just one. Yeah, it's straight 1-to-1. Thank you for that. If someone wants to fix that for me, thank you. We'll re-upload the slides after this, but it assumes the structure is directly related to Hooke's law. TLDR, if you double the load, you should get double the output, double the deformation. So for this first slide right here, and as Daniel pointed out, stress is directly proportional to strain as related by Hooke's law. So for this first one, we had 10 newtons, and we have, it's a little hard to read, it's a little crunchy, but we have about less than 3 millimeters, about 3.8 millimeters of deflection. If I go to my next slide, I'm now doubling that to 20 newtons, and I get just under 8 millimeters. There's going to be some rounding errors there, but it is a completely linear relationship. That's like one of the big assumptions when we're doing linear static analysis. The second assumption is, for when you're doing linear materials, it is critical that your material is elastic and you're only existing within the elastic region. If you exceed that, and we'll talk about this in a little bit, once you get past that strain, if you're doing a linear static case and you're looking for assumptions of like, okay, I actually want this to permanently yield beyond this point. If I was doing, I don't know what kind of study or something you would be doing that, you wouldn't want to use a linear elastic study because that's not going to give you accurate results, because once you get past that yielding point, it's still just going to continue that linear relationship, when in reality, that's not what we see. The second big assumption that I mentioned before, static. The static assumption assumes that a study in your case is time invariant. There is no change in the magnitude of direction of your loads. There's no change of the fixtures over time. The second part of that is that the loads ramp up slowly to the full magnitude, and your inertial or your dampening properties are ignored because they're small. So for like inertial forces, when you're moving your piece, F equals ma, those forces are entirely ignored, and you're only applying a single static load as if someone is just standing on the floor and not moving at all. The damping effects, let's talk a little bit more about that, but like you're pretending that there's only stiffness in your piece, and that's the only thing you care about. That ramping up slowly to your full load, that's what allows you to animate your SolidWorks studies. So like when you're like doing a static study, you notice an animate section. It's solving those for each of those discrete sections, but it's not doing it in discrete like time steps like it would for a dynamic study. It's just doing it like kind of frame by frame, so that you can get an animation. Also, for a lot of these slides, I'm just going to the either the SolidWorks or some other reference, and I'm just going to their like documentation page and throwing in assumptions if you want to read how they put it in their terms. A good way to think about static is like if on the left side you have considered I'm holding a weight above my arm, and I'm just holding it there, I'm not moving or anything like that, that's completely static load. If I'm moving it up and down, I need to consider like if I'm hanging on a beam and I'm just hanging there, that's not that much, that's a static load. If I start pulling myself up, the stress on that beam is going to start increasing. We are not considering the second part in a static load. Another way you can think about it is that like There's also a really fun. So I had a really fun time finding images for these slides. There are a bunch of wacky stuff out there, including just like stock images of people staring at static versus dynamic. Haha. But like a static load, if you're just sitting on the chair and not doing anything, it's completely staying. But versus if you have like looking at like analyzing different loads with time, like a loading curve, you need to do a dynamic study. Also just fun, weird shit. You're welcome to click through that. Actually, I'll do that right now. They have this like weird like story of this guy, if you're looking to understand mechanical advantage of sober Jeff is a static load, drunk Jeff is a dynamic load. And they had a bunch of fun stuff. So I would recommend that for fun. When you get outside of the linear static assumption and you're doing something more complicated analysis, you need to be aware of what, like, before you even turn on your software, you need to think about what study am I going to do. A lot of these softwares have help for how you would get there, but like you want to have an idea, and the purpose of today's lecture is just exposing you to different analyses that are out there. So like, how would you pick what analysis to do? What studies exist? What would Quishly do? So there's a bunch of resources out there that exist. Personally, one of my favorites comes from unexpected source, Fusion 360. Fusion 360 has a lot of really beginner-friendly visuals and documentation. I would not consider Fusion 360 a like state-of-the-art like analysis piece of software, but they do have analysis simulations, and they do have a lot of like really beginner-friendly stuff, like good UI. Also, with the education credit, you get unlimited cloud credits. So fuck it, put the these links are the overviews. I should change the hyperlink so it actually describes what it is, but they give like the documentation of what the different overviews are on all the studies, both for SolidWorks and Fusion. The cool part about Fusion is that when you boot up what study you want to do, they give you actual like images and like descriptions for what each of the studies are, so that you don't just have to like know that. So to get started, we're mostly going to be talking about structural ones. When you hear FEA, most of the time they're going to be referring to like structural analyses, but there are other types of analysis that exist out there. Static structure, exactly as it is. Will it fail when would deform excessively or just fail from static loads applied to it? We've discussed this already. There's plenty of examples like this. This was a knuckle done. Yeah. I very explicitly found that just for you. Here's a static load of a Baja knuckle turning, and we were looking at the spindle stress right there to see like how much light weighting could we aggressively get away with. And we've like, when just a static case right here, which is not really the case you want to do for a condition where you have like a moving vehicle, but for a pure static case, the stress is highly concentrated in the spindle and not the actual knuckle itself. So we could do a whole bunch of light weighting for that. Modal frequencies. If you have not taken ESA, this might be a little confusing, but basically all objects, dependent on their geometry and material properties, have certain frequencies that they will vibrate at and excessively deform at those vibrations. So like the most classical way to think about it is a tuning fork. When you hit a tuning fork, it's going to vibrate at its first natural frequency, and like excessively like vibrate at that frequency. You can solve for all kinds of weird geometries. You can solve what natural frequencies will exist. The basic concepts of this, and again, if you've already taken or you are about to take ESA, this will look a lot more familiar to you. But the basic concept you're taking is your mass times your force. U is again your displacement vector. The U dot is your velocity vector. Derivative position is velocity. Derivative velocity is acceleration. You solve all of that together, with M being your like similar to your meshing matrix that we talked about earlier last week, C being your dampening matrix. You'll learn more about that in ESA, and K being the stiffness matrix, the global stiffness matrix. This is by far the most classical example of modal analysis in frequencies. I forget the name of the actual bridge, but there was this bridge, suspension bridge built in, I think it was the 30s, that they did not do any modal analysis on. And with the wind pushing against it, it got near its resonant frequency and had a complete collapse. And they were lucky enough to capture it on video. But you can see in the actual FEA analysis right here, like you can simulate how these will deform and at various frequencies, what their modal shapes will be. So if you're ever working on like a vehicle or you're working on an airplane or something like that, you want to design your parts and figure out the natural frequencies and stay the hell away from resonant frequencies. Nonlinear studies. This is when we're starting getting a bit more advanced. When you are designing for something that you know will yield or has nonlinear material properties, you need to do a nonlinear study. Basically, these works when there's excessive deformation. So on the bottom left right here, a classic example is using a paper clip. If you push it enough, it will permanently yield. And you can do, the way that that works is it does very discrete steps. And it takes apart for how you're at a certain point in directions, you will no longer be linear isotropic, and you will have strain hardening in certain directions, and that it takes that into account by solving in discrete time steps. One example of a very nonlinear problem, this is something I worked on over the summer with Chris Lee and a few other owners. This is, and it's very confusing. On the left side right here, we have the cross section of a like infant's mouth and a pacifier. And if you guys don't know, pacifiers are actually really bad for babies, like from a dental hygiene or a dental dental perspective, because their soft palate is very susceptible to being deformed, because there actually is pretty crazy loads when just sucking on something. They were trying to design, there's a pediatric dentist at Tufts that's trying to design try to change the design of pacifiers that it decreases the amount of pressure that's put on the roof of the mouth. And so we ran a whole ton of like FEA studies, highly nonlinear because you're working with silicone rubber, which is a very hyperelastic material. So that's just one example of how these different types of studies exist in the real world. Doing a linear static assumption of this is possible. It's just going to give you kind of garbage results. Dynamic studies. So dynamic studies, the key thing right here is you want to think about time steps. So the classic example Fusion gives on the right is that you're having a football helmet that's receiving a sudden impact. On the bottom left, we have a really crunchy image of a car running into a wall in ANSYS. The key question here is figuring out what is my time step and what is my time scale going to be? And there are, we don't go into it, but there are like rules of thumbs for taking how big you want your time jump to be, because if you could have too large of a time jump and your results aren't going to be that accurate, and then too small of a time jump, you're going to be doing a lot of computational resources for it. The really cool part is you can do nonlinear dynamic studies. Whoa, were those two exact cases right there that we talked about earlier, where you have like either excessively yielding material or non-linear material, and dynamic events where you have like need to consider inertial effects or like how much something is going to spring back. These types of studies exist, and they've been done before. So here's another example of like real world, something that was done. Over the summer, Colin and I were working on a project at research at Olin where it was the Boston Scientific project from last year, if you were familiar with that at all. But basically, at one point, we needed to figure out, we have two silicon sheets, and we did an estimate of the magnitude of force that if I inflate them and they press against each other, how big is those contact forces going to be? This is a really good example of a nonlinear dynamic study, because you have highly nonlinear material. We're working with silicon. A dynamic project where you have to like consider both the inertial effects of how much it's resisting as you inflate it, and contact is a classic dynamic problem or nonlinear problem, where contact forces behave very weird. I don't understand the full math behind it, but if you boot up ANSYS help, you get a better understanding of how that works. How are we doing, y'all? Yay! Okay, about halfway through me talking and being boring. Buckling is a thing, and buckling is a really important thing to consider in FEA. If in the FEA, the real world, buckling exists because not all things are perfectly straight. If I have a really thin, long object and I press down on it axially, there's going to be some like curvature or like imperfection in how long it's going to be, and soon it'll start bending rather than just compressing straight axially. In the FEA world, you pretty much have near like identical that when that's simply not the case. Modal analysis studies do, where there's several, depending on your constraints, your length, and geometry, there's several buckling modes that will exist where you will have, you can buckle one way or another. So these are things that exist. Again, we just want to give examples. Topology and shape optimization. Second to last one. I'm almost done, I promise. Basically, if I have a object and there is a ton of unnecessary mass, how can I remove material from this object without compromising either my stiffness or my safety factor? So again, remember from the classic FEA like method where you go from displacement to strain to stress, you can maximize that stiffness and maintain the same amount of stiffness or a comparable amount with removing a lot of material that's just unnecessary for lightweighting. The disadvantage of this is sometimes it just gives you really unnatural shapes that are basically impossible to manufacture. So that's something to keep in mind. We don't talk about generative design, but that's also a disadvantage as well, where sometimes you just have to do additive manufacturing or have like crazy 6-axis machines, seventh degree rotary tables, yada yada. Okay. Other types of fun analyses that exist out there. ANSYS Fluent is the one I'm most familiar with for CFD. CFD stands for computational fluid dynamics, basically, or colorful fluid dynamics, because it gives you pretty plots and you have no idea if the hell it's right or not. But essentially, what you do here is that instead of discretizing and meshing geometry and applying the loads to it, you discretize the fluid domain. And then what you do from there is the governing equations are the Navier-Stokes equations. If you haven't taken transport yet, don't worry, you'll go over this in more details. The Navier-Stokes equations are basically really fancy ways of saying, well, for all fluid domains, you have to have conservation of mass and conservation of momentum. So like instead of doing all these crazy PDEs by hand in 1D cases or making really, really like big assumptions, because you can solve these from very simple cases of like a pipe flow and get a velocity profile if you make a few like assumptions. But for any real world example, there is just simply no way to solve fluid flow without doing some really complex PDEs. If you can figure out how to do it, you win $1 million. Literally, that's a challenge that exists out there. Thermal analysis is also something that can be accomplished through FEA or the FEM method. If you've taken when you take transport, I forget. I think we also did this in thermal. PDEs as well. Yes. You can, for a simple case, you can solve a heat equation, another PDE, for like a simple like 1D like element or a 1D rod or something like that. If you want to do a bit more complex geometry like this heat exchanger like right here on an engine or something like that, FEA is another way to go about that, just because like this would be hell to solve by hand. A really fun example that exists where you do thermal analysis is Chris Lee has an awesome assignment where you do the perfect mozzarella cheese stick. So Chris has a really big love of the mozzarella sticks in the dining hall, and so he had this really fun assignment in FEA where basically you want to design the perfect cheese stick. So you do like a really quick approximation. Ignore my shitty handwriting, but basically you're going to say this circular center right here, that's cheese. We're going to say it's water in this study. And then we're going to have a thin layer of crust on the outside of it. We're going to say that's bread. There's a really fun paper that he attaches for this homework assignment where someone did their PhD on flash frying McDonald's chicken nuggets. So there is hope for the world. But like you can do actual analysis of this. So you can figure out, you can see like you do a nonlinear dynamic study on this with thermal effects rather than loading effects, and you can see like you can get a temperature profile of a probe on like your temperature of the crust and the temperature of your cheese, and you can figure out if I just submerge this in this like vat of temperature this of whatever the frying oil is, how long am I supposed to leave it submerged before I have like a perfect melting temperature in the center? So really cool stuff that you can do, that you can start with just like basic approximations, compare to some like you can do a radial element for heat transfer. That's something you'll do in transport, and then you can compare that to like FEA, and you can see how close your models actually are. Neat stuff. Thermal stresses are also a thing. Rather than just looking at how much temperature changes, you can also look when you apply a thermal load to something, you will get a change in stress in the elements. Another really cool example of this is that they used to have bimetallic, or they still have them, but bimetallic temperature sticks, where essentially you have two pieces of material that you bond together that are made of different, have different thermal properties, and you heat both of them at the same time. One is going to expand at greater than one rate, and one is going to expand lower than one rate, and you'll get a radius of curvature, and you essentially have a beam bending problem that you're getting from, instead of applying a load, you apply a thermal mass. Yeah. And so these are also, I don't have screenshots, but this is also a homework problem in Chris Lee's FEA class, which is really cool.
One cool example of bimetallic strips is that like if you look at really cheap coffee like machines, the whole way that it like regulates flow is a bimetallic strip, or like really cheap rice cookers as well are using bimetallic strip.
It's cool stuff. Like there's really cool stuff, and like again, all these things, like you can start with very basic like geometry, and you can solve this by hand, and then create an FEA model and like validate your model, compare it to. Now if you're doing, this looks like some sort of impeller or something, I don't know where you would start that for by hand. Well, you could do testing. All of this is kind of like tip of the iceberg. This right here, if you boot up ANSYS Workbench, these are all of just the like, all of these are just the structural analyses that exist out there. There are so many that exist, and I think part of your like why we're doing this class and why we're doing such a short dip into FEA is we want to give y'all an understanding of like the types of studies that exist out there, and like an intuition for it, rather than just reading it and then having to dive through a ton of like hundreds of pages of documentation where you can have a quick kind of dip your toe into it. I've been talking for about 30 minutes. How are y'all doing? Doing good? Okay, I probably have another like maybe 15, 20 minutes of talking before we get to examples. So just power through, no bio break. Let's ride. The second part of today is we wanted to talk about mesh elements. So last week, we talked about solid element, shell element, and beam elements. These are the three main type of mesh elements that SOLIDWORKS uses. And so I wanted to go just a little deeper into what each individual one is. So these are the three elements, and on the bottom right here, you have the different like degrees of freedom for each element. But I'll talk a little more on that. Starting with solid meshing. Solid meshing is kind of like your de facto default mesh that your program is going to make, assuming you don't tell it anything else or you're not doing any weird geometry. If you're doing extrusions in your design, you're probably using solid elements. Solid elements, and if you remember from last week, we have usually first or second degree elements. First degree only has elements on, so all of these are first degree. They only have elements on the vertices of whatever, or they only have nodes, excuse me, on the vertices of the entire element. This is great for real quick, fast, and dirty FEA, but it also has some distinct disadvantages. For the left side, this would be a first degree element. On the right side, this would be a second degree element. SOLIDWORKS, they, rather than call it first and second degree, they have draft versus high quality elements. The difference is that they have nodes in the center points between the vertices. And that's really important because that's better for estimating and modeling curvature. If you have any weird curvature in your design, you are going to want to use second degree elements, at least for your final analysis, because first degree elements have a kind of bad disadvantage where they can't bend at all. The connection between the two will always be straight. So as a general rule of thumb, for the same mesh density and all other parameters equal, second order elements are going to be more accurate at the expense of you're pretty rapidly increasing your computational time. Because for each one of those nodes, for each one of your elements, you're now adding like at least 4 more nodes and 6 more degrees of freedom per node. So when you're doing quick and dirty, I just want to run my study and see if it gives me like something laughably unbelievable or within reality. I would do that, and then I would switch to a more high quality mesh element draft, or increase my thing and then walk away, and let it solve for like 6 hours or something. Another really important thing to talk about when you're using first degree elements and solid elements is a phenomenon called shear locking. Shear locking is something that occurs when you're only using first degree elements and your elements are behaving much stiffer than they actually are in reality, due to the way that the mesh is discretized. So to get started, if on the left side right here, I have just a standard element, if I'm putting it in pure bending, theoretically on the right, that's what my element should deform and look like afterwards. Where if I look at the center, if I do like center lines going through, I should still have right angles. And my top end here will be in tension and will be like increasing in curvature. And beneath my centroid, I will be in compression and I'm decreasing the length. When talking about first degree elements, remember, they are not great at deforming or doing any curvature. They will still remain straight between your vertices. And what that translates into in the actual study is that your element is now behaving much stiffer than it actually will in real life. So when you're doing an object and you have it in a bending load, if you don't have sufficient dense enough mesh, you can get a much higher you will get a much higher safety factor because it's not actually bending that much. Remember, from bending stress, a lot of the stress at the root of the tip comes from when you're acting in bending, and not necessarily just in pure shear. What a few ways to get around this. This can be prevented by, if you model, and this is a general good rule of thumb if you're using solid elements, you want to have at least 3 elements along the thickness of your beam or whatever you're modeling. That's a general rule of thumb you want to try to attend to at all times. You never want more than just you never want just 1 or 2 elements modeling the thickness of a piece. This isn't McDoes. No one element thick your teeth. Another way you can go about this is using second order elements. So make sure you sacrifice computational time, but now your element has a node in the centerpiece and it can bend. And lastly, the kind of easiest, fastest way to do it, and specifically why these exist, is you can use beam elements. Beam elements are a 2D abstraction of a 3D case, where you have a constant cross-sectional profile and you basically go from one node to the next, and the computer will save all the information of the second moment of area and the length and stiffness and rigidity. It'll save all that information with a constant cross section, but it doesn't actually have to model it. It just uses it as information. Beam elements are 2D simplifications, and they can resist axial, torsional, and bending loads. And so a beam element will have 6 degrees of freedom compared to just a regular solid elements where it only has 3. A solid element will only translate X, Y, Z, and you'll solve strain and stress from those translations, versus a beam element can now, depending on if you're doing a truss versus a true beam, it can either translate or rotate about that point. But because you're drastically reducing the amount of elements between the two, it greatly reduces your computational time and you can still get accurate loads. So here's an example of what it looks like going from a solid geometry to a beam geometry or a beam mesh. Basically, rather than having like a ton, like thousands of tiny little elements, you have two nodes, one here, and you connect the two with a straight line, and the computer will remember, okay, I have this cross section and I have to like define it in. If you are using weldments in SolidWorks, that was a concerning sound. If you're using weldments in SolidWorks with a predefined like cross section, SolidWorks will automatically calculate all of the cross sectional area, like information and material properties, and apply to that. And for now, a real world example, my better third, Colin.
Okay. And I'm going to talk about an example for a beam element analysis. But I guess before getting into that, why you might want to care, I guess, about my different element choices when you get to kind of like industry context, when I'm thinking about computation time and kind of the affordability of my model, you'll see that like solid elements are usually the last resort of options. Okay. And you'll find that like shell and beam elements are far more common, and that those are the ones that I'm usually using in order to actually like solve my model quickly and iterate on it. So that's why, at least for this model, we were kind of analyzing the different choices when it comes to using beam elements versus solid elements and how that actually changes my interpretation of results. So just for a point of context, this analysis is done per rules for the formula competition. We just have to prove that it is torsionally rigid and that it won't break on itself. So for the analysis, we did a study of comparing basically beam elements versus, and I changed this later, it's actually quadrilateral elements, which are like 2D like shell elements. And ultimately, the goal was just to compare how do these relative stiffnesses show us, how confident we are in the chassis, and how do these different loading conditions compare of, say, like tension versus torsion, and if that actually affects them equally or differently. And of course, we're just assuming that a higher mesh gives us greater accuracy and that we trust something that has a very fine mesh. So for the different loading conditions, we basically took kind of three boxes of the exact same geometry and just put them in different loading cases to compare beam versus shell elements. And this kind of gives us a basis of seeing like what is considered more stiff than the other. So you can see these are the meshes for the two different boxes when it comes to beam versus quadrilateral elements. And that'll be correct on the lecture day assignment now. And then also for this one, we're using what's called a split mesh, which is basically where I can like set like bounding lines and say for like, oh, my areas of interest, like at these weld failures or at my nodes, I want to have a really fine mesh, but say for where this kind of continuous area here, I'm saying, well, I expect this to be much easier to analyze, and I don't really need a fine mesh to properly represent this area. So you'll see that pretty common where I can kind of change my meshing to accommodate my different geometries or kind of areas of interest. So the bottom line is that we found that beam elements are 20% stiffer in torsion, 25% stiffer in bending, and 40% stiffer in tension when compared to actual quadrilateral elements. So that gives you a really different perspective of when I look at this analysis and I interpret what is safe. It kind of is drastic when I try to choose one versus the other. That is being said though, like you will not find, at least especially for like a space tube chassis, that we have to use like actual solid elements or shell elements. It will usually be beam elements because you'll treat it as kind of just a giant frame with a bunch of nodes. So I guess the bottom line is that yes, it is giving us stiffer results, but acknowledging that and being aware of that means that we can take that into account in our interpretation of results, and then ultimately, choose what makes sense for kind of the time that we need to use for actually doing this analysis, and ultimately how far off we are. Like it's probably more than safe either way. So it doesn't matter in the end which element we use, but it does change kind of how safe. But that's, I guess, basically the example. I think you'll find kind of considerations towards FEM
to be a huge thing when you actually go into industry context. Like, I don't know, I thought like a really cool example of something that I was just talking to Justin last night about was like he was doing representing like a welded joint with like a shell element that was just like literally just a single plane. Oh, I guess you can't see that. Which is just like a single shell element that I had to like represent like my weld bead. And like that was for using kind of like shell analyses to represent like gussets and welded joints and so on. And then like comparing if I have one giant face or if I split it up into a bunch of squares, like how does that change? And like these are studies that are done in industry context as well. Like, you know, how good is good and how do I compare it to my experimental results to say this FEM model is the best for what I have versus, you know, just putting everything as solid elements and calling it a day. Oh, sorry. And when I say FEM, I mean finite element method, if that wasn't clear to anyone. I'll hand it back to you.
Yeah. Colin was just talking about shell elements. Thanks for the setup. Shell elements are the third and final element type we're going to talk about today. Shell elements are super useful for when you need to model thin, constant cross-sectional geometry. So think sheet metal. Basically, you can represent, sometimes you'll call it surface elements. You can represent, and rather than going from a point to point, you can represent a small area with this, like with a type of element. Essentially what you do is that you take the thickness of whatever your piece is and you find the mid surface between those two. And then you can prescribe a given thickness to it. So like what shell elements are for is if you're doing a very like computationally heavy like material, something like rather than like modeling like a fine enough mesh where you have at least 3 elements across the thickness, you can abstract it to a shell element and prescribe a given thickness to it, and all those properties will still remain the same. So think similar to what a beam does and like a beam element does, where you have the second moment of area. You can describe the same exact kind of concept, but for a flatter like surface element. So for an example, what this looks like in real life is if I have this random sheet metal model here, translating that into a shell element, it just finds the mid surface between the two and automatically converts it. And if you're using SolidWorks or any other like 3D designer where you're using sheet metal materials, it'll automatically do this for you. And so you don't need to like do a ton of work. The only kind of like post-processing you need to do from geometry to shell element is that you want to make sure your orientation is the correct way. I will be honest, for a like isotropic case study, I'm not fully certain why this is important. But it is important that you make sure that like when you do, if I go back to the previous slide, you see how this section right here is green. If I were to flip the model over, it's also really hard to tell with the projector, but that side right there is also green. If I were to flip the model over, it would be entirely green. When you do shell elements, it gives you the top of the model and the bottom of the model. And if it'll make a guess for it, depending on your global coordinate system, if it's incorrect, all elements will have the ability within the screenshot, there's like flip sides for which way is up, which way is down. You guys, if you guys find a reason for it, I'd be very impressed and would love to hear more about why it matters outside if you're doing not an orthotropic case study. But it is important to remember in all the places tell you to do that. Some limitations of shell elements is that if you're doing any sort of thing that has like a T-joint or something like that, the intersection between the elements, so if I look right on this bead, are highly unlikely to be accurate. And if you're doing something of this case, it might be worth looking into, okay, if I actually really care about, say, I'm welding this or I'm doing something like this, if I really care about the stress along the root of this connection, it might now be worth it to look into using 3D elements or a beam. This would be a perfect case of a beam element, but say it's something really short or something like that. These are all considerations that you should take in of like, what element do I want to use and what are the limitations of that? Another example of a shell element was a case study of what I did 2 years ago. This piece right here is the splash guard on the Baja car. The splash guard is responsible for this tube right here is the fuel tank. The splash guard is if there's any spill of fuel while you're refilling the fuel tank, the engine sits right underneath in this small little pocket right here. The splash guard prevents any fuel from getting onto the hot engine. One of the rules and one of the tech inspection is that the splash guard must not allow any fluid to pool on top of it. So it can't sag and create any pockets. And during technical inspection, they literally take a water bottle and dump it over your splash guard, and it can't pool at all. All the water has to go off. My freshman year, my first year, we had like, this is, I don't know why, but they allowed like ABS and plastic splash guards, not metallic ones. And we had one. I didn't design it. I don't know. But it was pooling, and so we got rejected out of tech for it, and like we came around and literally had to hit the underside of it with a hammer a bunch of times to get it to bend back up until it would no longer pool. So when they redesigned the splash guard, one case study I did is I used a shell element right here. I also, it is a what do you call it? It's symmetric along this line too, so reduce computational time. I just put a symmetry pane right there. I'd like use a shell element and then apply a gravity of like 1.5 gravity load to see what my deflection would be, and if it's like, if I'm having it fixed, riveted to my chassis members right here, what my deflection will be, and if do I think that's big enough that it'll actually pool. If I was a bit more like looking back on how I would do this, and I highly recommend you guys do this, if like when you look at your earlier FEA studies and think about, man, I now know so much more stuff, how would I do this better? I would do this as a dynamic study, because the cars, like in the actual case of tech inspection, it doesn't matter because that's a pure static case right there. But the car like driving and moving around and having a bunch of loads that are highly dynamic, I would consider doing a dynamic case and still seeing, will this get to a point, or even looking into a buckling case like this to see if like it can buckle, go down. But that's another example of shell elements. We've been talking for way too long. Time to do stuff. On Canvas today, you kind of have a choose your own adventure type beat. Normally, this is 2 different days. And so full credit again goes to Chris Lee. Beam elements, you have a simple just C channel where you can have SolidWorks give out a bending shear moment diagram. You have, so that's what this like little rainbow guy is right here. You have a conveyor belt assembly or a conveyor frame assembly where you can see how beams connect and intersect with each other and do loads there. You also have a standard like default, like I think someone from SolidWorks made a Baja frame. This is not Olin Baja's frame. You could also look into modal analyses for that and see how that works, which I think is really cool. It gives you spaghetti chassis.
There's also a free Ansys tutorial on both Baja and
Yes.
chassis analysis.
Yes. Very cool as well. And for shell elements, I didn't get any screenshots of it, but essentially you can represent, there's a tube that you're torquing and it also, this tied into connections in FEA as well. So if you look at how you would simulate a weld bead with shell elements, I would recommend looking at the shells as well. But we're just going to walk around and help you all as needed. Before you get started, just some kind of closing remarks for the day. On Monday, there is not a prescribed lecture. We're just going to have open time to either do homework corrections or work on your tool sheet. We'll also probably discuss the finals and like what like the remaining class schedule for this class is going to look like. Also a reminder, we're killing quizzes. We're no longer doing quizzes. Sorry, we should have announced that earlier. Just we don't think it's worth it. But we'll fix all the Canvas grades and everything like that. I know like right now in Canvas, you'll have very few grades. So if like that one random quiz might be dragging y'all down. Also submit homework questions.
I will say a lot of grades have not been given. We're trying to get better on getting homeworks out this week and this coming week. So I know you probably don't have homework 1 or homework 2 graded. But just know that we're working on it.
I'm guessing if like we're talking grades initially, we're probably take some time, but what is the timeline look like for like correction grading?
I mean, I think it's just, I guess within reason, like if you're submitting like in the last couple of weeks before school ends, we could probably not post 12 time to grade it. So I guess it's like, you could just, you can keep submitting many times until the like very end. It's just, I guess giving enough time to then iterate upon regrading. Does that answer your question?
Cool. There will be no homework for FEA. just heads up, next week we are getting into wear and fatigue, in SN curves and what else? Fun stuff.
I also just linked on the dis. There's this blog called Enter FEA that
I love that blog.
It's really good. It has like really high level explanations of FEA like concepts, and they do a good job of taking practical considerations. So if you kind of want to just understand like nonlinear versus linear, like types of dynamic analyses, like that's a good place to start it.
Making my dreams come true. Ooh, I'm gonna-
No. I was like, sorry. What we did in the past. Really.
My dreams come true.
A lot of people that haven't seen a lot of things. Over there. Yeah. I mean, so. Or three, four, or the. Yeah, it's hard to picture stuff, which when you guys have conversation, that and then no TA. Yeah. Well. It's like, I want to ask Chris, but sometimes I don't even know. Yeah. Oh, yeah. If.
He's dancing.
Not have, like, oh, yeah. Why is this chassis so like.
It's, yeah. I'm actually curious, how tall is that chassis? Because it looks tall.
What's the difference? Like the rear box. They're active. 0.82. Maybe the sides of the cockpit are really low. So it's like here, like straight, because also this is a frequency study. So yeah, it's gonna get like. I understand that I'm not productive. Yeah, so it doesn't give you. What's the like?
Of the engine. So I mean, to be honest, for Baja chassis, I'd be shocked for any sort of frequency that like we're even close to it, because this is what. Actually, I'm gonna do this.